The recording, I've actually run out of space on my laptop. So that's the only place I can put this. I said this one. The proton NMR spectrum of compound E is the solvent. It's a solvent CdCl3 is shown. The molecular formula of compound E is C9H10O2. Okay, so this is about NMR spectrum. Remember, in NMR spectrum, you always use a deuterated solvent, which should not have hydrogen, because otherwise the solvent itself will start resonating. We are not analyzing the solvent, so we don't want the solvent to resonate. So it's always going to be a deuterated solvent. Okay, that's one thing. I said next is, so it's a deuterated solvent. The next thing is, explain why CDCl is used instead of CDCl3. So it does not resonate. So it does not show up in the NMR spectrum. Next thing is, explain why TMS is added to give the small peak at chemical shift delta 0. So TMS is a molecule that is added along with compound E. The sole purpose of TMS is a reference. It's used as a reference. That's it. TMS is tetramethylsilane. It's a molecule which has this formula. It's got silicon and it's got 3 CH3s. 4 CH3s actually. So it's got 4 CH3s, and so since it's got 4 CH3s, the TMS is going to show a peak, and all the other peaks are calculated in reference to this one. So it has no purpose at all in analyzing the NMR spectrum. The only thing is that it's used as a reference. So it's got a chemical shift of 0. Now, compound E is hydrolyzed by hot NaOH, giving 2 organic products. Only one of these products is ethanol. Name the functional group in compound E that is hydrolyzed by hot NaOH. So there's alkaline hydrolysis that is happening. So you have to figure out what the functional group is. So can anyone tell me, like, what it breaks down into 2 groups? So that's E. That's the molecule. So a lot of things get hydrolyzed. They break down into 2 pieces. This must be an ester. When an ester is broken down, it's either an amide or an ester. But over here, it must be an ester because there is no nitrogen, so it must be an ester. So it will break down into 2 pieces. One is, he said that it was ethanol. So one of the sides that it will break down into is ethanol. So how many carbons are we left with? We're left with 9 carbons. So the other side must be a carboxylic acid. So it must be a carboxylic acid. And since it's an alkaline hydrolysis, it will not be a carboxylic acid. It will form a salt of the carboxylic acid. So it's going to be CO -1, Na +1. And you'll be left with how many carbons in this part? We've got 3 already. So there would be 6 carbons. I'm just going to write R at the moment. So remember, an ester breaks down into a carboxylic acid and an alcohol. Is this part clear? You clear? Is this part clear?
Yes, sir.
We'll count. It's going to be, I think, not 7, 6. Okay, there's already 3 carbons over here. So then you have, I think I'm recording this one. So name the functional group that is present. That must be an ester. With 2 oxygens, that's the only thing we can come up with. Then he says, describe and explain the splitting pattern, the peaks delta 1.4 and delta 4.3 splitting pattern at. So I think, and you have to give the reason for splitting as well. So at 1.4, that's a triplet peak. Now, when do you actually have a triplet peak? When the neighboring carbon atom has. So when your neighboring carbon has 2 hydrogens. So it must have a CH2 neighborhood. And what other peak is he talking about? He's talking about the peak at 4.3 as well. So at 4.3, this one is a quadruplet peak. You can see 4 peaks over here. So this one over here, that's a quadruplet peak. When you have a quadruplet peak, when the neighboring carbon has 3 hydrogens, so that means it's got a CH3 neighbor. So one of the peaks is a triplet peak, the other one is a quadruplet peak. You've got a triplet and a doublet again after that as well. So that's the answer to this part. Do you get, this thing. Now each molecule in the compound E contains 5 protons, which give rise to the peaks between 7 and 8.5. 1 second. How free there. Actually, each molecule of compound E contains 5 protons, which give rise to the peaks between 7 and 8.5. 7 and 8.5. So there are 5 protons, 2 different peaks. And it then states, identify the functional group in compound E which contains these protons. And he's talking about a single functional group, I think, or which contains these protons. So, and he's talking about E, 5 protons. Now, one thing is, if you look at this molecule, can you identify which protons are going to have these 5? And I'm thinking that he's grouping them together. Now, for this, you would probably need a data booklet first. So let's, I think the data booklet is already open. This one. So where's the NMR? That's carbon 13, this one. So first thing, look at the peaks. Where are they forming? They're forming around 7 to 8, somewhere around that. So 7 to 8, which, remember, we've only got oxygens. So that's out of the question. The others are out of the question, 7 and 8. So the only one left is benzene. Is that clear? Because I don't think any other hydrogen protons is falling within the 7 to 8 range. Okay, so it must be a benzene. So if I go back, 7 to 8, that's definitely benzene. And I can confirm that there are 5 hydrogen protons that belong to benzene over here by looking at the ratio. When you have carbon and hydrogen ratio, and it's a very small ratio, almost 1:1, that indicates that there's benzene present. Because benzene mein, it's only carbon and hydrogen have 1:1. So there must be a benzene over here. So these 5 protons, they probably belong to benzene. So that's the answer to this part. Here again, 1 mark for that. So this one is benzene. TK, we've answered that. Now give the structural formula of compound E. So we now have to make the structural formula of compound E. So we got pretty close to it early on, that I knew that it was an ester, which was forming ethanol, and the rest of the carbons were on the other side. So we're going to start making that. So the ester had this thing, that on one side it's going to have ethanol. So that's your ethanol with the hydrogens. And on the other side, I'm going to be left with 6 carbons. There were 9 carbons in total. So those 6 carbons must be part of the benzene structure. So, and they're going to have 5 hydrogens. And there's going to be a benzene ring. And that's the only possible structure that's possible in this case. ठीक है, is this part clear? ये clear है सारों को?
सर इसके साथ एरे हम लोग नहीं लगाएंगे?
नहीं, एने तो वो लगा था when it broke down, जब उसका hydrolysis हुआ था ना, when it got hydrolyzed, then this side became a salt of the carboxylic acid, and that side became became ethanol. Okay, so that is when Na came along. Is this clear?
Yes, sir.
तो उससे E की बात की है. अच्छा, then you have the next part, which is the mass spectrum of compound E includes fragment ions with Me values of 29 and 77. Give the so mass spectroscopy and fragments. So this molecule will break down when you do mass spectroscopy. TK, remember that's a separate thing from NMR. When you do mass spectroscopy, the molecule breaks down into small pieces. Which small piece of this molecule will have a mass value of 29? TK, C2. I mean, this piece might break down and the mass spectrum might detect this, and that's C2H5 plus 1. That's exactly equal to 29. What is 77 then?
The benzene ring with the carboxylic acid group.
I mean, what's C6H5? That's sorry, C6 is 72. 5 H's. That's no, it's just this part. That's going to be equal to 77. I think that's 12 into 6. That's 72, 73, 74, 75, 76, 77. So this thing over here. So it's C6, H5, and don't forget to write a positive charge on top of it. Is that clear? As the next one. So we're done with this question. Question number, whatever this question was. The question number 10 is, you have to figure out the polymerization. Complete the table by identifying each type of polymerization. So an alcohol, a diol with a carboxylic acid, what type of polymerization would you have? I mean, that's condensation. Like when you have an alcohol and on the other side, you've got a carboxylic acid. So it's going to form a polyester. The OH and H are going to be lost, water is going to be produced, and you're going to have a condensation. So it's gonna, just to be on the safe side, I haven't checked the marking scheme, but just to be on the safe side, write condensation polymer, and to be very specific, it's going to be a polyester. The next one is going to be exactly the same. When you have an acyl chloride and an alcohol, you pretty much get the same reaction. The only difference is that on one side, you've got a Cl, an acyl chloride. So the H and Cl are going to be lost. And again, it's going to be a condensation polymer, and it will form a polyester back again. And the last one is an alkene. Iska main check karunga, वैसे should we use the word condensation over here, or the last one is addition? ठीक है, the last one is definitely addition because you got two alkenes. The alkenes are I think these two carbons have a double bond, and they've got a CH3 on one side and H on one side and two fluorines on the other side. So the molecules are just going to get added up along the double bond. So that's your addition polymer. So iska bas mein, let me just check. Yep, condensation, addition. That's it. Okay, nothing else. Next one is 2-aminopropanoic acid can polymerize under suitable conditions. No other monomer is involved in this reaction. Draw a section of the polymer chain formed, including 3 monomer residues. So basically, you have to draw 3 monomers. Clearly identify 1 repeat unit. So 2-aminopropanoic acid can polymerize, and there's no other polymer. So we're basically making a peptide. So an amino acid has a carboxylic acid group on one side, and it's got an NH2 group on the other side. and it's got a CH3 on one side, and it's got an H on one side. I mean, focus on this carbon atom. It's got NH2, COH, and CH3 on one side. And you're going to draw 3 of them. So the next one will kind of be exactly the same, NH2. You'll have CH3 on one side, carboxylic acid, and an H. And then you're going to have another one, TK, similar to this. Let me draw this. And they're going to form a condensation polymer. The OH and H are going to be lost. So the middle part, the OH and H is lost. The OH and H, they'll form water. It's a condensation reaction, and they'll all link up. And that's going to be an amide linkage. So, and he's saying that it's not just 3, it's a section of the polymer chain. So there's a lot of them. So the H and OH have to be lost from the ends as well. So we're going to remove those. Make sure you draw continuation bonds, because the same thing will happen at the other end as well. So there's going to be linkages that will be continuing. So that's your 3 marks, TK. So remember, we're just drawing a section of the polymer. And
Sir, is this a polyamide?
it is a polyamide. It's a peptide. It's a protein molecule. Now he says that 2-amino-propanoic acid exists as 2 stereoisomers. Draw the 3-dimensional diagrams to show the 2 stereoisomers of 2-amino-propanoic acid. State the 2 stereoisomers, type of stereoisomerism shown. So it's optical. TK, that's one thing. It's going to be chiral. We can draw one of them. In chiral, what you have is you've got H on one side, you've got carboxylic acid on the other side. You've got NH2 on one side, and you have CH3 on one side. So there's going to be a mirrored version of the same one. So I'm pretty sure you can draw the mirrored version yourself. So there's going to be a mirrored version of this molecule.
Sir,
Yes.
does it matter which way the dotted line and the triangle are? Like if you put it on the other side?
It doesn't matter. It doesn't
Okay.
even matter where you put the mirror as well. Like if you put the mirror on this side, that's left to right. Laterally, it's going to invert, right? You could have drawn an upside down mirrored version. Like if you put the mirror this way, so it's going to be vertically inverted, right? So that also does not really matter. Or one way to mirror is like, imagine that the mirror is actually the plane of the paper of the screen. Like imagine the screen is the mirror, right? So if it mirrors front to back, then the molecule would actually look like this. That what will happen is that the one going behind the page, that will become CH3. And the one coming towards you, that will become COOH. That is also a mirrored version. Okay, so it's not, so you got lots of mirrored versions. I mean, there are many ways of drawing a mirrored version. The one that you know of is just flip it laterally, right? I mean, get the carboxylic acid on the left and the NH2 to the right. You can do the same thing vertically as well. And you can do the same thing if you think of the screen as the mirror. Then the bond that's coming towards you is the one that's going to be going behind the screen, and the one that's behind the screen, that is the one that's going to be coming towards you. Is that clear?
When there is a question related to stereoisomerism, like can we write optical?
This is optical. Well, in optical, you have got chiral centers, right? As the next one is type, and it's going to be optical. Now, the skeletal formula of this is given when W is mixed with second compound called a hardener. A polymerization reaction occurs, producing a non-solvent-based adhesive. Give the name of this type of non-solvent-based adhesive. This is no longer really in your course. Okay, these were super glues. So you're saying W is mixed with a second compound called a hardener. That's no longer in your course. So what was W, by the way? Just a second. Did you mention what W was? I said, anyways, this is W, sorry. So, but I'll give you a brief idea of what superglues are. Okay, so if we just confirming, I mean it is superglues, allow superglues. So I'll give you an idea. You can remember this is no longer really in your course anymore. They've actually removed anything that says superglues. I'll just double check if. Pretty sure last I remember the superglues are no longer in your course, but I'll just give you a brief idea because questions similar to this might still appear. No, glues I can't really. No, that's giving me 0 results. I say anyways, but I'll give you an idea of what a superglue is. There's a thing called cross-linking that's related to polymerization. Although it's no longer in your syllabus in the latest one, but it's still very similar to what your syllabus is. So you might, just in case, might get a question similar to this. So here's what the idea is. That let's say I've got a polymer chain. A polymer chain has, let's say it's a polymer chain that's an addition polymer chain. And every time the polymer chain has a carboxylic acid that's coming out of it. And this thing is repeating over and over again. So there's another, it's got a carboxylic acid, TK, let's draw that, and so on. So it's repeating. And there's this other carbon chain, which is kind of exactly the same. So let me just copy that. So there's this other polymer chain. So there are multiple polymer chains. And this one might have, I mean, it might have the carboxylic acid group pointing in the upward direction. So let's say there are 2 strands of polymers. Now, a glue is basically when whenever you have any epoxy or super glue, it's basically 2 strands that are very strongly attracted to each other. Now, at the moment, the carboxylic acid groups will be very strongly attracted to it by hydrogen bonding, but hydrogen bonding is itself not very strong. It's very weak. So according to intermolecular forces, that's going to be a relatively strong attraction, but it's not strong enough. It's not glue-like, right? Glue is like really tough. Okay, they would be very strongly bonded to each other. So polymer strands, they attract each other. But at the moment, the attraction is not that strong. Now, what happens is sometimes when you have a glue, you mix a molecule, and that's a molecule that creates crosslinks. So for example, I'm going to mix a molecule which is a diol. So it's got OH groups on both sides. Now what this molecule will do is that an alcohol reacts with carboxylic acid, and this alcohol will react with this carboxylic acid. So the OH is going to be lost and the H is going to be lost. The carboxylic acid OH is lost, and the H over here is also going to be lost. Eventually, previously the 2 carboxylic acid were not reacting with each other, but they ended up reacting with this other molecule, which is known as a cross-linking molecule. And they've ended up forming an ester. The carboxylic acid reacted with the alcohol, ended up forming an ester. The carboxylic acid over here reacted with the alcohol and ended up forming an ester. And that results in the creation of a crosslink. So now it's not just weak intermolecular forces that are attracting the two strands. Now the two strands are kind of bonded to each other. So, and now it's glue-like, now it's hardened. It's like, I mean, the two strands are now like permanently bonded to each other. So they've kind of become one strand now. Okay, so is the idea of a super glue clear? Okay, what's a super glue? Just the basic idea. Is this clear?
Yes, sir.
And Arzoa, it could be between anything. Over here, it could be anything. I mean, it's just the idea that you've got one polymer strand and you've got another polymer strand. If the two polymer strands or their side chains, they bond with each other, then the chains will be permanently bonded to each other, and it would be very hard to actually separate them. So just the idea. So it could work in a number of ways. I mean, you could make up anything, and the two things can react with each other. And sometimes you must have seen that when you make glues, like the tough ones, like epoxies and super glues, you add another chemical into it. It's always a mixture of chemicals. So you add a bunch of cross-linking molecules. Those are very important because they create those cross-links. And that's how the structure becomes really hard, and it completely. There are actually two. There's a water-based glue. What happens in water-based glues are that they're weak. In water-based glues, what only happens is that if the water evaporates, the strands kind of come close to each other and they sort of have stronger intermolecular forces. In these cross-linking glues, where you add another chemical into it, they permanently bind with each other, and that makes it a lot harder. But anyways, again, this is no longer in your course. It's not mentioned in the syllabus. But it's a very simple idea. So maybe you might get a question. Most likely, you're not going to get a question on this. Most likely, you'll just get simple polymer questions. That's it. Okay, so coming back to the question. He's saying the hardener is a diamine, has an alkyl chain with two amine groups which are not bonded to the same carbon atom. Draw the structure for that would make a suitable hardener. So we can leave this question. We can let's try and solve this. By the way, W is a mix with a second compound called a hardener. A polymerization reaction occurs, producing a non-solvent based adhesive. We did this super glues. A hardener is a diamine. A diamine has an alkyl chain with two amine groups, which are not bonded to the same carbon atom. Draw the structure. So basically, he's given you the whole description. So you just have to draw the structure. So he said that it's an alkyl chain. The hardener is an alkyl chain, and it's got two amine groups which are not bonded to the same carbon atom. So let's bond one over here and one to the other side. So I guess that's it. That is how he described the hardener over here, the diamine. So that's about it, just one mark. As anyways, let's move on. TK, we're done with the last two questions, TK, previous ones. Nee, there's no reason for that. He just said that there's an alkyl chain. It's got two NH2 groups, and that's it. The two NH2 groups are not bonded to the same carbon atom. So next one, question number 8. Benzene reacts with bromine in the presence of a suitable catalyst, forming bromobenzene as one product. Gives the name of the other product. So what happens when you have, what's the other product when you have an electrophilic substitution?
HBr.
Do you get the other product is HBr. And you can't have opened the notes. TK, it's this reaction that we're talking about. 1 second. Where's benzene? I mean, this one. ठीक है, bromination of benzene. AlBr3 is the catalyst in this reaction. So you're being asked to draw the mechanism. So the mechanism is that the Br plus one gets attracted to the benzene, and the Br then bonds with one of the carbon atoms, and the benzene electron cloud becomes partial because the Br took electrons away from it. And in the next step, the H is the one that actually returns the electrons. So the H then gives its electrons back to benzene. Name the mechanism. That's electrophilic. Substitution. The next part is step one. How do you attach a carbon chain to benzene?
Is this alkylation, sir?
Okay, that's alkylation. What you do is, okay, that's alkylation. What you do is you just need a Cl with the carbon atom. And this one has 2 H's, and you got 3 H's with this one. So what will happen is that the carbon over here has a partial positive charge, and the benzene is going to be attracted to the carbon, and the Cl over here is going to get knocked out. So that's alkylation. Halogenoalkane is needed, and the catalyst is AlCl3. That's what your catalyst is. When you oxidize an arene, a benzene with a carbon chain, what happens? With KMnO4. Okay, and let me open the chart as well. Okay, that's oxidation of the carbon side chain. That's yours. This one, I think, spider chart. So oxidation of the carbon side chain. So this is alkylation. Benzene, you attach the carbon chain, that's alkylation, FeCl3, KMnO4. The carbon side chain breaks away and it just leaves you with a carboxylic acid. That is what's going to be happening. Okay, so it will form a carboxylic acid. So this molecule over here will turn into a carboxylic acid. What happens? How do you turn a carboxylic acid back into an alcohol?
Excuse me, sir.
हाँ जी.
Sir, OH, हमारे पास, if the OH is present, so why wouldn't it wouldn't turn into the carboxylate ion? Because we've seen that before.
हाँ, ठीक है, सही. नहीं, that's true. You've got alkaline. ठीक है, remember, it's whenever you've got alkaline conditions, so it's always going to result in the formation of a salt. ठीक है, very good. That's what the answer is. Not a carboxylic acid. ठीक है. And next one is, and that's correct. ठीक है. And the next one is carboxylic acid turning back into an alcohol. That is reduction. So it's going to get reduced back into an alcohol, and the reducing agent is going to be LiAlH4. Okay, that's going to be reduction.
Sir, could you repeat this step 2?
No, that's this step. Okay, let me just show you. That's AS. Whenever you have carboxylic acid, if you add LiLH4, it turns back into an aldehyde, and the aldehyde with LiLH4 turns back into an alcohol. If you remember, AS primary alcohols turn into aldehydes, and aldehydes they turn into carboxylic acids when you oxidize them. The reverse is they turn back into an aldehyde, and the aldehyde goes back into turns back into a primary alcohol. Is that clear?
Step 2.
You're talking about step 2?
Yes, sir.
Step 2 is simply this one, that whenever you've got an alkyl side chain to benzene, that's an arene. Whenever you have that, KMnO4 acidified and reflux, that will result in the formation of carboxylic acid. The side chain will just break off and it will just turn into a carboxylic acid. You don't need to know the mechanism. Just remember the fact that the alkyl chain, wherever it is in the benzene, or attached to the benzene, it will just turn into a carboxylic acid. Is that clear?
Yes, sir.
The only thing was that the conditions that they gave us was alkaline. So that means under alkaline conditions, you're not going to have carboxylic acid because the acid will eventually end up reacting with the alkali. So you'll have a salt of the carboxylic acid, not the carboxylic acid itself. Then reduction happens. It should, I mean, it should behave in exactly the same way. Because the, I mean, it doesn't really matter to the carboxylic acid is always losing and gaining H plus ions. Like it's an acid, right? So it's always kind of losing H plus ions and always gaining H plus ions back again. Achha, then the last part, how do you get rid of the benzene? Like how do you get rid of the double bonds? And so that is hydrogenation. That is just hydrogen with nickel catalyst, and the temperature is going to be 200 degrees centigrade. Okay, so that's simple hydrogenation. Ye wala step hai. Where's this one? Benzene turning into becoming saturated.
Sir, its bond angle is 109 degree.
Now it's saturated, so it's sp3 hybridized. So I think we did answer all the question. He's just asking for the reagents and catalyst, draw the structure of A. We did that as well. So we answered most of it. Identify suitable reagents for step 3 and 4. We did that. Deduce the number. This one. Deduce the number of peaks in carbon 13 NMR spectrum of cyclohexyl methanol. Which one is cyclo? This one. So how many carbon environments do we have? There's this carbon that's different from all the other carbons, right? So it's got a unique environment. Then these two carbons have exactly the same environment. Then I have these two carbon atoms having exactly the same environment. Then you have there's this one that's got a different carbon environment. And then you have the last one that's going to have a different. So how many peaks? That's 1 resonating, 2, 3, 4, and 5, right? I mean, this will resonate at F1, this will resonate at F2, this will resonate at F3. This is F4, and this is, so 5 frequencies. So carbon in total has 5 different environments over here. So 5 peaks. These two are exactly the same environment, right? I mean, this carbon and this carbon, they are exactly the same, bonding wise, right? Unki bonding dekho na, they're exactly bonded in the same way. Like over here, carbon is with 2 H's, right? And the neighboring environment is exactly the same for the 2 green ones. Ki agar yahan tak jana na, so you have to travel the same distance. Or over here, you travel the same distance. So they're exactly identical. I mean, this one is different. The blue ones are different from the green ones, right? Because the blue ones are closer to CH2OH, so their environment is different from the green ones. So you got 5 peaks. So that's it. So that was question number 10. I said this one now. Okay. Phenol can be made from phenylamine. Give the reagents and conditions. So how do you convert phenylamine into phenol? Phenylamine is, so we can just look at the chart. This is what you're going to do. So how do you convert phenylamine? This is phenylamine, NH2 with benzene. What you're going to do is you're going to turn it into a diazonium salt. So it's going to be NaNO2 plus HCl, and the temperature is going to be less than 10 degrees centigrade. It will convert it into a very unstable diazonium ion. And then hydrolysis. If you warm this diazonium ion with water, hydrolysis happens and it will decompose to form phenol. So those are the 2 steps that you are required in this question. So that's 2 marks. ठीक है, लिख लेते हैं. First thing is step 1, NaNO2 plus HCl, and the temperature is less than 10. Second, hydrolysis. So it's water plus heat. Next one is phenol reacts with dilute nitric acid under room conditions to give a mixture of 2 isomeric products with the molecular formula C6H5NO3. Use the data booklet to draw this. So first thing, phenol, is it 2,4,6 directing or is it 3,5 directing? Kya the phenol, is it an activating group or a deactivating group?
Activated.
Okay, that's an activating group, and because the lone pairs on oxygen, they overlap with benzene's electron cloud, so the electron density becomes higher on positions 2, 4, and 6. Or yahan pe bhi hoga, the electron density will become higher at positions 2, 4, and 6. And NO2 is going to get attached to either position number 2 or 4. I mean, yahan pe it's getting attached to 4 over here. Let's attach it to 2. And the name of the molecule will be over here, it's 4-nitrophenol. And over here, it's 2-nitrophenol. क्योंकि data booklet में ना लिखा होता था, it used to be, now you don't have a data booklet, by the way. So in the data booklet, they actually told you where exactly, which ones are 2,4,6 directing groups and which ones are 3,5 directing groups. So they used to tell you in the data booklet. But even in that case, you don't need to refer to the data booklet because you already know it's 2,4,6. Phenol reacts with an excess of aqueous bromine, draw and name. Now, also remember, phenol is a very activating group. So what happens is that when you react it with bromine, the electron density in phenol is so high that bromine gets attached to all 3 positions, 2, 4, and 6. So this one is going to be called 2,4,6 tribromophenol.
So the upper one is dilute.
Yes, that's probably dilute. But reason I was able to figure out that there was only one NO2, it's dilute aqueous nitric acid. Iske andar bhi na, if you had, where's phenol? Just a second. This is phenols. I say even in this case, if you had phenols, right? If you use dilute nitric acid, then it's going to be just one NO2 mostly. If you had used concentrated nitric acid, then NO2 is going to get attached to all 3 positions. With bromine, you're going to get attached to all 3 positions, and it will give you a white precipitate, which is a test for identification of phenols. So he was using dilute nitric acids. You were getting both of them. As I described, 2 visual observations that can be made when it reacts with an excess of, first thing, bromine gets decolorized. Second one, white precipitate. So I think remember the other one, that Br2 gets decolorized as well. Write an equation for the neutralization of phenol when it behaves an acid. So phenol is C6H5OH. Remember, phenols are weakly acidic, so they react with bases. And the H will combine with the OH and they'll form water. And you'll have a salt, which is sodium phenoxide. The phenylamine also gives the same test. So you're saying that why it's I mean, you can say it's a test for both. Okay, both for phenols and phenylamine. Or we can even generalize it further. I mean, in your course, it's just phenols and phenylamine, but it's a test for identifying any very activated benzene. The next one is water, phenol, and ethanol behave. So this is about acids. I'll just so this is about acids, and the comparisons of weak acids. So remember, when you talk about acids, where's the start? Just a second. So remember, you've got 4 types of acids. You've got a carboxylic acid. That's relatively the strongest acid. Phenol slightly weaker. Alcohols very bad acids. They don't really behave as acids. So you've got you need to know this table as well, that when it comes to acids, carboxylic acids have pretty much all acid reactions. They can react with sodium, NaOH, Na2CO3, and NH3. So they can have all 4 reactions. Phenols can only react with strong bases and with metals, reactive metals, but not with weak bases. And alcohols pretty much have no reactions with bases. They react with very reactive metals. So the question, coming back to the question, we have to give the explanation as well. So the strongest in this is going to be phenol. Water is going to be in the middle, and alcohols are going to be really bad acids. Now, what's the explanation? The explanation for phenol is that when a phenol loses its H+1, the negative charge overlaps with benzene, which makes the negative charge small. On the other hand, when you have an alcohol like ethanol, like CH3CH2OH, when it loses the H+1, the alkyl chain has an electron donating effect, which makes the negative charge large. So alcohols tend to have a stronger OH bond because there's more attraction. Phenols tend to have a weaker OH bond because of lesser attraction, which is why. So how would you describe this in words that that the lone pair on O in phenoxide, which is C6H5O minus 1 ion, it overlaps with benzene's electron cloud. Reducing the negative charge density. Let's just read it from there. ठीक है, phenols का कहाँ पे है? Lone pair on phenoxide overlaps with benzene's pi electron cloud. Charge density on phenoxide ion decreases, making it more stable. There's less attraction for H+1. The OH bond weakens, hence there's going to be more dissociation. नसीब वो ethanol में मसला ये कि ethanol के केस में there's an electron donating effect, so which kind of makes the negative charge even greater. So that would lead to a stronger attraction for H+1. So alkyl chain has an electron donating effect, which increases the charge density on the negative ion, making it unstable. Stronger attraction for H+1, less dissociation, and the OH bond strength increases. So compared to water, so water is like in the middle, but over here you've got an electron donating effect, which kind of increases the negative charge, which kind of increases the strength of attraction between the O and H. So which is why it leads to even lesser dissociation. Is this part clear?
Yes, sir.
So now next one. अच्छा next कहाँ पे गया? अच्छा I mean that was it I think. So ठीक है, we're done with this. We're done with question 7, 8, 9, and 10. Just a second. So ठीक है, let's continue with the same paper tomorrow then. ठीक है. Or बस ठीक है, अभी tomorrow we'll continue with the same paper. Okay, everyone, take care.
Thank you, sir.
Hafiz.
Hafiz.